Hi, everybody. My name is Salari. I'm CEO and founder of Quaxys. We developed the next generation of quantum hardware for control and measurement of qubits. Today, I'm going to talk about quantum information processing with superconducting qubits. In the first few minutes, I'm going to talk about how a quantum computer looks like, what is it good for, and also different platforms for quantum information processing. After that, I'm going to focus on superconducting qubits. Unlike the microscopic world we experience, atoms have an uncertain existence, meaning they can be here and there or this or that in the same moment. This is called superposition, and it enables us to do many things simultaneously. Using this quantum multitasking, we can build computers that do computations that no classical computer could do. So the first thought about utilizing quantum effects for performing computations with quantum objects was proposed by Feynman in 1982. Maybe this question that how should a quantum computer look like? David DiVincenzo has answered this question with his 5 criteria for implementing a quantum computer. According to these criteria, we need a scalable physical system with well-characterized two-level quantum systems called qubits. It is also necessary to be able to initialize a quantum register to a known value before the start of computation. And we need a set of universal quantum gates to which any transformation possible on a qubit can be reduced, meaning that any other unitary operation can be expressed as a finite sequence of gates from this set. We saw part of this in the previous lecture study. And finally, we need to be able to read out the results of the computation. And all this must be done with high fidelity and sufficient speed such that decoherence processes do not destroy the information. Once we have such a set implemented in a system, every conceivable quantum algorithm can be implemented using this type of system. Well, now that we know how a quantum computer would possibly look like, the next question would be probably what a quantum computer is good for. Certain quantum algorithms can be done with an unprecedented speed, which is impossible to reach by their classical counterpart. An example is a quantum algorithm proposed by Peter Shor, which finds the prime factors of an integer number. Simulation of quantum systems is another application of a quantum computer, which could revolutionize chemistry and the production of new medications. However, keep in mind that quantum computers are not necessarily faster than classical computers in all types of computations. Actually, in certain types of computations, they are much slower. It is also good to know that quantum circuits can perform all the operations performed by classical circuits. As mentioned earlier, any two-level quantum system can be used as a qubit. This can be polarization of a photon, spin of an electron, flux or charge of a superconducting circuit, and there are also other options. This slide shows various types of qubits. Of course, each qubit has its own advantages and disadvantages. For example, photons interact weakly with each other, and they are easily lost, whereas electrons and solids naturally interact and readily exchange information with each other. On the other hand, photons have desirable properties. For example, they are the preferred choice for sending quantum information over large distances. Some scientists also think about hybrid systems where the advantages of different qubit platforms are combined into a single system. Now we're going to talk about capabilities of superconducting quantum processors and also a little bit about quantum supremacy. The quantum supremacy happens when a quantum computer can carry out a task beyond the means of today's state-of-the-art classical supercomputers. The first quantum processor which proved the quantum supremacy was made by researchers at Google. This processor used only 53 superconducting transmon qubits to perform a very specific computational task. And solving this task takes about 200 seconds for the quantum computer, whereas it would take approximately 10,000 years for the state-of-the-art classical supercomputer. This slide is more for the people who are interested in doing research on experimental aspects of semiconductor qubits, such as spin qubits or superconductor qubits. When you're working on superconducting quantum computers or even spin qubits, there are 4 areas that we need to master. So these are shown in this slide and include nanofabrication, cryogenic techniques, microwave techniques, and data acquisition and measurement. I explain a little bit about nanofabrication. Electron beam lithography and photolithography are used to write patterns on a sapphire or silicon substrate where the wafer is cut into chips using a dicing saw. And the electron beam lithography is used to fabricate nano-sized devices such as the superconducting Josephson junction. We will talk about this later, where nanometer resolution is required, something in the range of 50 to 100 nanometer. And the photolithography is used to fabricate the components with a larger size, such as microwave resonators, transmission lines, and those kind of components. In electron beam lithography, an electron beam is used to write the patterns instead of UV light for the photolithography. After developing the pattern, the aluminum is deposited using thermal evaporation or e-beam evaporation techniques. Of course, other metals can be deposited, for example, niobium, but aluminum is mostly used for superconducting qubits because it's cheap and easy to evaporate, and it has a very good qualities for superconducting qubits. After liftoff, the pattern is created, and we can start doing the next process, which is using microwave techniques and put the chip in the dilution fridge and using various cryogenic techniques in order to do measurements and get the data. Now we want to understand how we can build an atom on a chip. So because an atom is inherently a two-level system, can be used as a qubit, and we want to see how we can use an artificial atom to do quantum computations. So the energy levels in an atom are non-equidistant. This is a characteristic of atoms, which allows unique frequencies between different energy levels. For example, in hydrogen atom, where each transition corresponds to light emission at a certain wavelength. So an atom can be modeled as an anharmonic oscillator. So in an anharmonic oscillator, we have non-equidistant energy levels, as shown in this slide. So being anharmonic is related to also nonlinearity in the system, and is essential for making a qubit where we can isolate the first 2 energy levels with unique transition frequency. And these 2 energy levels correspond to 0 and 1 states. If we can make a system which mimics an anharmonic oscillator with non-equidistant energy levels, then we can say that we have made an atom artificially. This is in fact possible with the help of a nonlinear superconducting element called Josephson junction, which can be considered as a nonlinear inductor. And if we connect the Josephson junction in parallel to a capacitor, then we have an anharmonic quantum oscillator, as we see here. So what we see here is in this slide is a comparison between a simple LC circuit, which is a harmonic oscillator with equidistant energy levels. And we see also a capacitor in parallel to Josephson junction, which makes anharmonic oscillator with unequally spaced energy levels, where we can isolate the first 2 energy levels and use it as a qubit. One of the promising types of superconducting qubits is called transmon qubit. And transmon qubit has a transition frequency from the ground state to the excited state at microwave frequencies around 5 gigahertz. So frequencies in the microwave range are appropriate for most of the solid state quantum devices, also spin qubits. These frequencies are high enough for the standard cryogenic techniques to be used, yet also low enough that makes fabrication of circuits much smaller than the electrical wavelengths visible. And the equivalent circuit of the anharmonic oscillator is a capacitor in parallel with 2 Josephson junctions. The 2 parallel Josephson junctions, as we will see later, they form a SQUID. And by applying an external flux using a coil, the transition frequency of the qubit can be tuned. So using 2 parallel Josephson junctions gives us tunability. So here we see an implementation, real-world implementation of the equivalent circuit using interdigital capacitor. In figure B, you see interdigital capacitor, and in the middle you have 2 Josephson junctions in parallel. And so this is nothing more than a parallel LC circuit with a nonlinear inductor, which is Josephson junction. And on the right-hand side in figure C, you see that different energy levels with their corresponding transition frequency. And as we will see later, this transition frequency is proportional to the geometric mean of the capacitor and inductor characteristic energies, which are EJ and EC. EJ is the Josephson energy and EC is the charging energy. So we'll see later how this transition frequency is calculated. Now we're going to explain a little bit about how the Josephson junction makes a nonlinear inductor and how it can be designed. So a Josephson junction consists of 2 superconducting electrodes with a thin insulating layer in between. The Josephson effect occurs at very low temperatures, which the junction becomes superconducting. In this case, the Cooper pairs become the charge carriers and can tunnel across the insulating barrier. And in order to reach those kind of temperatures, we need to use a special fridge called dilution fridge to cool down the junction below its superconducting critical temperature. And so in this kind of fridge, we use the cooling effect. We use the cooling effect which comes from thermodynamic processes in helium-3 and helium-4 mixture. So at this point, we want to see more about the physics of Josephson junction, but we don't want to dive deep into the physics of it. What is insightful here is the relations, the last relation between the Josephson inductance and the Josephson energy. As we see that LJ, Josephson inductance, is inversely proportional to the Josephson energy. And this will determine the transition frequencies as we see later. In order to make the transition frequency of the qubit tunable, 2 Josephson junctions in parallel are used, which is called SQUID, superconducting quantum interference device. And the Josephson energy or the critical current of the SQUID can be tuned using the magnetic flux that goes through the SQUID loop, which in turn changes the transition frequency of the qubit, as we will see later. Okay, the charging energy is given here, and see that the EC, which is the charging energy, is the electron charge squared divided by 2 times the capacitance of the transmon qubit. For the transition frequency of the qubit, we obtain a familiar formula for the resonance frequency of parallel LC circuit. So as we see here, the omega 01, which is the transition frequency from the ground state to the first excited state, is given by the familiar formula of the parallel LC circuit, which is 1 over square root of LJ CT. And we see that it's also related to the Josephson energy EJ and charging energy EC. The transition frequency can also be tuned using the flux. As we see here, omega q is the transition frequency from ground state to the first excited state. And this can be tuned by square root of cosine p phi or phi naught, where phi is the flux going through the SQUID. So the geometry and parameters of the Josephson junction and the capacitor, they can be engineered to reach the desired transition frequency, which lies in the range of 5 to 7 gigahertz. Also note that the ratio of the Josephson energy to the charging energy must be in the range of 20 to 100, typically 50, where it is called the transmon regime. We see it also here, where EJ over EC is equal to 50, and this is how the transition frequencies look like. This regime is very interesting because the sensitivity of qubit to charge fluctuations is highly reduced, where the charge fluctuations are responsible for decoherence of the qubit. So decoherence happens, the qubit loses its quantum information. However, we need to be careful that there's a trade-off between the sensitivity to charge fluctuations and anharmonicity of the qubit. So this means that if you increase the ratio of EJ over EC, the sensitivity to charge fluctuation decreases, so the qubit coherence time will increase. However, this also results in decrease of anharmonicity, meaning that energy levels approach the equidistant region with increasing EJ over EC ratio. So here we see the anharmonicity. Alpha is defined as difference between the energy from the ground state to the first excited states and first excited state to the second excited states, which is proportional to the charging energy. Now I want to talk a little bit about what we're doing at Quaxys and how we help researchers and companies to accelerate their R&D in the field of superconducting quantum computers. Quaxys provides hardware and software solutions for quantum technologies, especially for quantum computing. And our current focus is to facilitate research and development of superconducting spin qubits. As you know, early computers were large, consumed huge amount of power, and needed lots of human intervention to operate. So current quantum computers are somehow at a similar stage, and therefore we need integrated, affordable, and efficient solutions. Quaxys technology integrates the microwave front and backend into a single module, which can be configured according to the requirements and needs of the research and industry. So in the bottom left picture, you see comparison between the size of Quaxys hardware, which is in blue, and the current technology, which is in red. Maybe it seems that such a significant size reduction is not a big deal for large labs, but think about the future and scaling of quantum computers to thousands and millions of qubits. Then such a significant reduction in size is essential when we want to scale quantum computers. Our first product is called Conver 4840. It's a modular solution for control and measurement of qubits. And it is the interface between the dilution fridge and room temperature control software. The Conver 4840 consists of the components such as low noise amplifiers with tunable gain, IQ mixers with automatic calibration, band pass filters, low pass filter, attenuators, RF sources, arbitrary waveform generators, and this can be configured according to the needs of the researchers. We also have a dedicated software, you see in the bottom right hand side, and also Python library, where people can use Python library in their Python codes and use various functions for control and measurement of qubits. So the combination of Cloudberry 4840 and our software package simplifies the control and measurement of qubits significantly, where the software allows to choose among various measurement scenarios with a single click. So as we see here on the bottom right-hand side, we have different measurement scenarios, and just by one click, you can run the qubit control and measurement scenario. So thank you for your attention, and if you have any questions, I would be glad to answer.
Thank you, Alan, for the information. Great. Any questions? If you have any questions, you can unmute yourself and ask, or put it in chat.
Can I ask a question?
Sure.
I'm sure you guys can hear me. So can you talk a little bit more about the measurements in the superconducting qubits and how it's controlled by your hardware?
Yes. So regarding the measurements, we have this box here, which is the Cloudberry 4840. As said before, you see different connections here for the fridge, where the output of the fridge comes into this box, and it gets amplified using low-noise amplifiers and goes to, for example, IQ mixer for the down conversion. And it has outputs for the ADC, analog to digital converter. It goes to analog to digital converter, down convert. It will be down converted. It goes to the analog to digital converter for the further processing. It has also inputs and outputs for network analyzer and spectrum analyzer, where you can use, for example, network analyzer to measure the resonant frequency of the resonator for readout resonator, and it has also inputs for the AWG, arbitrary waveform generator, and RF source, where you can up-convert the signals using, again, IQ mixer, which is this kind of modulated signal is used for the control of the qubit. And it has also output to the fridge, where you can combine different types of signals, like coming from AWG, spectroscopy signal, RF signal, and all those kind of things. And this is connected to, so you put, this is a plug and play box. You just put this box in the lab, connect your microwave cables, and start doing measurements. Using this software, which you see here in the bottom right-hand side, you can simply click on control and measurement scenario, certain control and measurement scenario, and just everything will run automatically without code or anything. But people who want to use Python code, they have also a library for that. They can include their library into their codes and use the functions there. Just call those functions, and control and measurement of qubits can be done automatically.
Okay, thank you. And also one more question. So the system now is designed for qubit, right? You want to access the ground and then the first excited states, basically your control, the operation and the measurements. Since we have the higher levels, do you think how realistic to operate on the higher level, access to higher level, and also measure the states if the system occupies the higher levels?
You mean transition?
Yeah, in the transmon, you not only have 2 levels, right? You have more levels.
Yeah, that's correct. So your question is whether we can also measure the other transition frequencies?
Yes.
Yeah.
Say if somehow I can excite the system not into the superposition of the 2, what about superposition of all 4 levels? And it's the principle allow us to measure that states.
And that's doable with spectroscopy of the whole range of the qubit. So what you do is that the first step is to characterize the qubit. And what people do is to do a frequency sweep in order to see different transition frequencies. And actually at higher levels also and higher powers, very interesting nonlinear effects appear. And also people use that for other types of sensing and computational applications. But this is definitely possible to characterize the higher transition frequencies by using a frequency sweep.
All right, thank you so much.
You're welcome.
Any other questions?
So I know this is targeting for microwaves, but I'm just curious what the exact frequency range does the device operate linearly?
It's in the range of 4 to 8 gigahertz.
All right, thank you.